Hello, Chemistry 12. This is Mr. Chan here, and today is the second lesson on reaction kinetics. And what we're going to be focusing on today is we're going to be talking about collision theory. Now, last day, remember we talked about reaction kinetics is basically talking about how a reaction or how fast a reaction proceeds. Now, what we're going to do today is we're going to be focusing on sort of why reactions occur at an atomic level. The first thing we need to understand is that when we talk about reactions, in order for a reaction to occur, particles must collide. Okay? And in this particular case, this is key. If there are no collisions, there is no possibility for a reaction to occur. If you think about this in your life, for you, if you want to get a job, if you want to meet people, what you need to do is you need to introduce yourself. Okay. If you don't introduce yourself, if you don't put a resume out there, there's no chance for you of getting a job ever. So that's the same idea here. So for a reaction to occur, particles must collide. Now, when we talk about collisions, when they collide, there are two conditions that must be met. First, they must have, oopsie, yeah, they must have sufficient energy and the correct geometry for a reaction to be possible. Okay, now when we talk about sufficient energy and correct geometry and related to what I had talked about, it's like when you apply for a job, you have to be qualified. Okay, you have to have the right qualifications and you have to apply at the right time for you to get a job. And that's the same idea with sufficient energy and correct geometry. So for particles to collide, they must have enough energy and they must collide at the correct way. If they don't have enough energy or they don't collide the right way, even though they might collide, there would be no reaction. Just like for a job, you might apply, you might apply, but if your resume isn't up to speed or if you are applying when a company is laying off people, you won't get hired. Now, when we talk about sufficient energy, what happens is the minimum kinetic energy that is required is called the threshold energy. Okay? And when we talk about a rate of reaction, the rate of a reaction depends upon the number and energy of effective collisions. Now, if we were to take a look at this, when we take a look at collisions, a lot of the collisions fall into this sort of bell-shaped curve. So here, a lot of times when we talk about collisions, what happens is they fall in this sort of bell-shaped curve. Now, so what happens here is in a bell-shaped curve, it sort of takes a look at all of the collisions. Now, a lot of the collisions would be in this area where I would call the good try. They collide, but they do not react. Okay. Here, in this particular section, this is where you have reactions. So these ones in this area react. The separation between the two of the good try and the ones that react is this little arrow here, and this is what we call the threshold energy. And depending on whether or not you have enough energy, or if you do not, that allows you to fall under the good try for particles, or do you react? And so the shaded area is all those particles with enough energy to react. Okay. Now, the peak right here, this is the average energy. Okay. And so what happens is this. So what you have here is you sort of distribute all of the particles And those with lower energy is basically under the good try. Okay. And those that have a higher energy are the ones that react. Okay. So on the x-axis, what you have is a ranking from low to high energy. And on the y-axis, what you have is the number of particles. Okay. Now, an example would be like this. A lot of you are planning to apply for post-secondary. All of you will apply to all of the universities like UBC, SFU, U of T, McGill. All right. A lot of you will apply, and some of you, if you have all the requirements and meet the minimum expectations, you folks will get that wonderful acceptance letter saying, congratulations, you've made it into UBC. That is like the particles that have enough energy and they react. Okay. Now, some of you who apply may not meet all of the requirements. And unfortunately, you folks will get the rejection letter saying, oh, thank you for trying to apply to UBC or SFU, but unfortunately, you don't get in. Those would be the good try. Okay, so that would be an example. Thousands and thousands of kids apply for UBC and SFU, but only those that have enough energy or have the minimum requirements are able to get in, while those that do not meet the minimum requirements do not. That's the same idea with particles. Millions and millions and billions of particles collide, but not all of them react because they may not have enough energy, okay, while some do, and that is what we call our reaction. Now, so today's lesson is going to be based upon how do you read sort of this bell-shaped curve, okay? And so when we talk about reaction kinetics or collisions, we take a look at the factors that affect the rate, and we are going to relate it back to the sort of bell-shaped curve that you see up here. Now, the first thing and most common one that we talk about is concentration. So in this case, when we talk about concentration, the rate increases with an increase in concentration. Why? Is because there are more particles that can result in more effective collisions. Now, what happens is generally gases and solutions fall in this category, but not solids. Why? Is because solids have a constant density and as a result, a constant concentration. So if we were to take a look at the bell-shaped curve, okay, so what you have here is I have the normal concentration, then I have a higher one and a lower one. Now, in this particular aspect, what you want to do is focus on this. Okay, come on. We focus on this particular area. Okay. And in here, what you want to do is you want to look at the number of effective collisions. Now, you will notice that with a higher concentration, notice the shaded area here is higher, is more. So therefore, what happens is you could think of it, the concentration, the higher concentration means, let me get here, an increase in the number of collisions. Therefore, a higher rate. So when we have something of a higher concentration, okay, why is it a faster rate? Is because of the fact that there is more effective collisions. Okay. Now, notice with the lower one, if I were to highlight the lower one here, why is it a slower reaction with a lower concentration? If you look at the number of effective collisions, especially in this shaded area, you notice it's a lot smaller. Therefore, it is a slower rate. Now, not only do you look at the number of effective collisions, but notice here, you notice that this shaded area here that I'm going to highlight, okay? So here, you notice here, I'm going to put a little star. The higher concentration also results in more ineffective collisions. So a thing that you need to be aware of is, yes, when we increase the concentration, yes, we have a higher number of effective collisions, therefore the rate is faster, but you also have a higher number of ineffective collisions, and as a result, you have a lot more what I would call dead weight. An example would be like in a class. So let's say I have a class of 30 students. I have, let's say, 6 students that get A's. That would represent the number of effective collisions. So I have 6 students with A's, 24 students that don't get A's or dead weight. Now, if I were to double my class to 60 kids, I might get 10 or 15 people that get A's. So I have a higher rate. But now, out of the class of 60, I now have 45 students that do not get A's. That would be like my dead weight. So that's the one thing that you need to realize that, yes, when you increase the concentration, yes, the rate is faster because there's a higher number of effective collisions, but you also have to keep in mind that there's also a higher number of particles that do not have effective collisions. And this will play a role later on in our next unit. Now, the other thing that you should be aware of is up here, notice the peaks of each of the curves. And in this particular case, I'll just put it in a different color. The average energy stays the same. Okay. So the average energy stays the same. So the number of particles have gone up or gone down depending whether it's a higher concentration or lower concentration, but the average energy of the particles in general for that given reaction stays the same. So again, are you able to read this particular kinetic energy diagram and relate it to what we had done here? Okay. Now, another factor that affects the rate is surface area. So let me just get this here. Now, for surface area, the rate increases with an increase in surface area because why? There's more exposed area for collisions to occur. Now, the one thing for you to be aware of is this. The distribution curve does not change because the energy of the particles has not changed. Okay? And the other thing is this only affects heterogeneous reactions or reactions with different phases. Now, I want to go back to the idea where the distribution curve does not change. Okay? That is where it is different than concentrations. So what happens is with higher and lower concentrations, you notice the height of the kinetic energy diagram has gone up or gone down. But when we talk about surface area, it is basically exactly the same. Okay. Now, let me give you an example of why it would be exactly the same. So let's say we have cube sugar versus powdered sugar in coffee. You know instinctively that the powdered sugar dissolves faster, faster. In this case, why? Because more simultaneous collisions occurring. The key word here is simultaneous. So if you had two identical cups of coffee and you put powdered sugar in one and a cube sugar in the other, you will instinctively know that the powdered sugar dissolves faster. The reason being is because you have more exposed area. The energy of the coffee, the energy of the particles in the coffee do not change. The energy of the sugar does not change. And so this is why the distribution curve does not change. It's just that you have more simultaneous collisions, and therefore, this is why the rate increases. The energy, again, the energy of the particles has not changed. It's just that you are getting more and more simultaneous collisions. The example would be like if you went shopping at Superstore. Okay, so let's say you have one or two lineups and one or two cashiers opening, and people are lining up. It's a lot slower. But if you had 7, 8, 9, 10 cashiers open, you know that the speed of the lineup will go a heck of a lot faster. Not because people are spending more, but it's just that more people are getting through at one time. They're still spending the exact same amount, but they are simultaneously being rung through a lot faster than if you only had two cashiers. That is the same idea. With the powdered, what's happening is there's more simultaneous collisions, all right, than a cube of sugar, but the energies are exactly the same. The other one, the third one, is the temperature. What happens is for temperature, you will notice that the rate increases with an increase in temperature. Why? Because the particles have more energy and collide more. Now, unlike concentration, the key thing is this: the fraction or percentage of effective collisions has increased while the overall number of the particles stay the same. Okay? The overall number of particles stay the same. Now, generally, an increase of 10 degrees Celsius will tend to double the reaction rate for slow reactions because the increase in the fraction of effective collisions will be greater. Now, what I want to do is I want to talk about this in terms of temperature. Now, the first thing you will notice is, again, it says here you have a greater fraction. The key word here is, let me just do that. Keyword here is fraction with enough energy to react. So again, you notice here the shaded area is a lot more with an increase in temperature. So you do get a faster rate, just like what you have up here with concentration. Notice you have more of a shaded area, so therefore a faster rate. But what's the key difference here is notice in this particular case, what you have is you have a shift in the average energy. Okay. Now you compare that to when we did concentration. Notice the concentration, the average energies or the peaks of the bell-shaped curve remain almost the same. So in this particular case, what happens is you get a shift in energy. So in this particular case, the red line, this has a higher energy because it's shifted over towards the right. Now, an analogy is this. So if we were thinking about temperature versus concentration, you could think of the analogy like this. Whoopsie, analogy. Okay. If you have a temperature, what happens is like you increase the hours of studying. A concentration would be like an increase in number of students. Now, what happens is both of these, both result increase the number of A's of A students in class, but what happens is, increase in temperature increases the class average. Okay. So in this particular case, what you see is that when we talk about a greater fraction with enough energy to react, that shaded area is like increasing the number of A students in the class, but the shift in energy is like increasing the class average. Okay. So in this particular case, when we talk about concentration, it's just like increasing the number of students. But here, what's happening is we're talking about, hey, increasing in temperature would be like telling the students to increase the number of hours of study. Both of them will result in more students, but increasing the number of hours of studies will also increase the class average. Now, please make sure you notice the difference between the number of students and class average. Okay. Now, what I'm going to do is show you something in your textbook. So if all of you can take a look on page number 18 in your Hepton textbook, if you take a look on page 18, they talk about the average energy of the molecules. And middle of page 18, what they will do is they'll show you this particular diagram. Now, you notice what's happening as you increase the temperature, 25, 200, and 400 degrees Celsius. Notice the average energy of the system is increased, okay? Now, but also what's happening is you are increasing the number of effective collisions at 400 degrees compared to 200 compared to 25, okay? So again, this is looking at the kinetic energy diagram. Now, if you take a look on the bottom, it says for a slow reaction, a 10-degree increase in temperature doubles the rate of a reaction. Okay. Now, how do they explain this? Is because in this particular case, let's say you have a slow reaction. First of all, why is this a slow reaction? Is because if you take a look, notice the number of effective collisions here. This area here is really tiny. But notice if they blow it up, if you increase the temperature, the area of effective collision for a slow reaction is actually double. So if you take a look and read through what they say on page 19, it says, in this particular case, since there are twice as many molecules of B which have sufficient energy to react, the rate is double. That is only key for a slow reaction. And a slow reaction means that it doesn't have very many effective collisions. Okay. Now, the fourth one, we talked about temperature, we talked about concentration, we talked about temperature, concentration, surface area. The last one, couple I want to talk about is a catalyst. So what is a catalyst? And some of you may have been exposed to this in your biology class. Okay, a catalyst is basically a substance that speeds up a reaction without being used up. Now, how does a catalyst work? Is a catalyst changes the way a reaction proceeds, which result in a reaction with a lower threshold energy. The key word is that it changes the way a reaction proceeds. Okay, now, so what you notice here is that when you take a look, you have a catalyst threshold energy versus a regular threshold energy. Now, notice the catalyst threshold energy is a lot lower. So in this case, if I were to use an analogy, it would be like Metrotown. Let's say you're planning to go to a store, let's say the Apple store in Metrotown. There are two different ways to get to the second floor. One of them is using an escalator, and the other one is using the stairs. Now, the catalyst, this would be like using the escalator. At Metrotown. Why would it be like an escalator at Metrotown? Because in this particular case, it's a lower threshold energy. All of these shoppers at Metrotown don't have to use that much energy to get to the second floor. While the stairs, this would be like the regular threshold energy. Okay, so this would be like the stairs. And you will notice a lot of people do not take the stairs at Metrotown. Okay, so a lot slower rate. All right. Now, so that would be like a catalyst. It changes the pathway. For the stairs, you would have to go at Metrotown. Apparently, there are two stairs. One is the theater area, and the other is by the bus loop, right? You notice a lot fewer people choose to take the stairs. A lot more people choose to take the escalator, even though it might be, an extra 2-minute walk. Now, the one thing that you need to be aware of is this. Only temperature, and I wrote it down here. Only, let me just, only the temperature and the catalyst affects the fraction of effective collision. Okay? The catalyst actually changes the threshold energy, while temperature changes the fraction of effective collisions or the ratio of effective collisions. Okay? Surface area and concentration do not. Okay, so please be aware of that. The only thing that changes the fraction of effective collisions is temperature, because you're changing the ratio of effective collisions versus ineffective collisions, and the catalyst, because the catalyst changes the threshold energy. Now, the last one is the nature of reactants. Some substances are just simply more reactive than others. So in some cases, if you have a low threshold energy, notice I've highlighted it here. Low threshold energy, it is fast or spontaneous because you have lots of effective collisions. Are you able to relate those three terms together? Here you have a higher threshold energy, slower or non-spontaneous, few effective collisions. So if you are looking at the number of effective collisions, notice the low threshold energy is fast, considered fast because you have lots of effective collisions. Okay. And in this case, an analogy would be like this. A low threshold energy would be somebody who is impatient. They blow up very quickly. Here you would have somebody who is very patient. Why? Because they're very slow. They have a high, tolerance for idiocy or something like that. And so we call them, very patient. Example would be road rage. Some of you might have family members that go from 0 to I am really mad when they're on the road. That would be like having a low threshold energy. While you have some members of your family that are like, do, 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 do. Oh, it's okay. Traffic is slow. That's okay. And so on. They are uber patient. I'm sure some of you know of people who are impatient and some of those that are very patient. And that's like having a low threshold energy, which are impatient people, and high threshold energy, which are very patient people. Now, there is a YouTube, video that I do show. So you can take a look at this. I'm going to see if I can share that, with you. And that will illustrate a slow versus fast reaction due to the nature of reactants. So if I have that here, so this is talking about the alkali metals, and I'll see if this works. So it will start. Okay, I'm going to stop it here. I'm going to let you folks go through that video yourself. But if you take a look, especially if you start at around, I don't know, minute 127, you will see the difference between some nature of reactants, which are very slow, versus something that can be a little bit more explosive. So I'm just going to leave that up to you for you folks to take a look at. Okay, so that's that video on this YouTube channel. All right, my friends, that will be it for today's lesson on collision theory. Again, my suggestion would be if you have any questions to come and see me during flex time or lunchtime or during class, to sort of go over any of the questions you may have had from this particular section. All right, my friends, thank you very much. Have a good day. Bye-bye.